Alright, so hello everyone, this is the 14th session, and today we're going to learn something very important. I would say that this is the single most important distribution in statistics, and it's used everywhere. So if this is so prevalent in our daily lives that I think this is one of the things that everyone has to know. But um, I'm not sure in Tanzania, but here in U.S. in the U.S. not part of the core curriculum. Um, but nonetheless, this is a very important lesson. So let's just get started without any further ado. And before talking about the normal distribution, we're going to talk about something called binomial distribution. All right. All right. So let's just get my pen and let's see what this is all about. So first of all, um, let's just recall something. So let's say we're tossing a coin, and let's say that x represents number of heads. Okay, and probability of getting a head is since it's a fair coin. This is a 0.5. All right, so this experiment or this trial is called the Bernoulli trial. Sorry, Bernoulli trial. Okay, and this is when you have two possible outcomes. All right, so either success or failure. So there are only two options. Okay, and success with probability of p, we denote it as p, and failure, of course, it would be 1 minus p, or sometimes we note it as q. Alright, so again, probability has to add up to 1, so p plus q again is 1. So this is a Bernoulli trial when you flip a coin once, or when you I don't know, when you roll a die and x represents getting an ace, or just one. All right, so something like that when you have two outcomes. All right, so for Bernoulli trial, we just where's my pen? The parameter again is a measure that determines the distribution is just p, because everything else is here. Everything else, such as q, we can infer that from p, right? So we just need p for Bernoulli trials. All right, so that was Bernoulli trial, and Bernoulli trials are very simple to look at. And if we were to do this multiple times, so if we were to say flip a coin 5 times, then we call that a binomial distribution. So binomial distribution is n independent Bernoulli trials. Alright, so if you're looking at this, binomial compared to Bernoulli trial, binomial distribution has two parameters, and those are n and p, because we need to know how many times we're flipping the coin, and we need to know the probability of getting heads. So the parameter here, parameters are n and p, and here is one thing that's very, very important to note, is that this is independent. We've mentioned this before with mathematical definition, but it's saying that previous trial does not affect the next trial. So say it doesn't matter if you're getting heads in the second trial. On the third trial, you'll just have you'll just begin as if it was new. So it's not dependent on the previous case or any future cases. So it's independent. That's why we can multiply the probabilities here, and that this is very important to know. So whenever we're discussing distribution, we have to look for this keyword independent, or else it's going to be very, very messy. But most the cases where we are going to deal with is all independent, so we're just assuming independence for everything. All right. So let's just look at an example to note this. All right. Let's see. Okay, so let's say we're looking at an example. All right, so this is an example. Say yeah, let's just do this. All right, so say x, random variable x, represents the number of students who prefer news from the internet. Okay, and here n equals 4. So we're looking at 4 students. All right, so and we say P, the probability that student preferring news from the internet is, let's just note it as P for now. All right, and let's see how that works. So here the outcome, the success is preferring the internet. And the failure will be what? Not preferring everything else. So not. Alright? So X is a student who preferred news from the internet. So let's just look at different cases. So when X is 0, okay, we have X equals, and then we have 0, 1, 2, 3, 4. These are all possible cases for the sample space X. So it's going to be, for if it's 0, it's going to be what? 4 students, all of them are fail. So I'm just going to denote this as S, success, and F as failure, right? And if it's 1, you can have S, F, 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 F as S, sorry, F, F as F, and F, 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 S. Right? Let's, if you have 2, it could be S, S, F, F. What else? F, S, F, S, F, S, F, F, S, F, SSF, and this, right? Do I have all of them? Yes, I do. 6. And here it's the same thing. We're going to have 3 successes. Alright, so, and lastly we have 1, 2, 3, 4. Alright, so these are all possible cases. For x. Okay. So when we are looking at the probability, alright? So say we're looking at the probability. So say probability of x equals 0. And we already mentioned that probability of success is P, and probability of, this is success, and probability of Q is failure. So using these two notations, we're going to have, this is 4 of them. Oh my god. Okay, hopefully it will work again. We have 4 failures, so that's going to be Q to the 4th, right? And what about this? When x equals 1, we have 3 failures, so Q to the 3rd, and we have 1 success, so that's P. But here we have 4 different cases. It depends on where the success, where the position of success is. So we have 4 cases to choose from. So what we do here, since we have 4, because we have 4 students, and we're just choosing 1 to be the success, so we do 4 choose 1. So this is going to be what? 4 times Q to the 3 times P. Alright, same concept here. When x equals 2, we have Q squared, P squared, but we're choosing 2 out of 4 to be the success, or the rest to be the failure, right? And that's why we get 2 P squared Q squared. 6 P squared Q squared. And same thing here. When x equals 3, this is going to be 4 choose 3 P cubed Q. So this is 4P cubed times Q. And x equals 4 is, again, just P to the 4th. Or you could write this down. If you generalize this, it's going to be the following, right? So this is a definition of binomial distribution. And binomial distribution is described by this function. We call this f of x, and we're going to learn this later on. We call this probability function, probability distribution function. So let's write this down as this. And probability of x, the random variable x, equals to the little x, which represents a number, right? Is n choose x times p to the x times 1 minus, it should be 1 minus p. One minus p to the n minus x. Alright, just using the above, this is going to be what? If probability of x equal to 2, this is going to be 4 choose 2 p to the second power and q squared. So this is the probability. that we use. Okay, so let's just do an example. All right. So let's look at an example with actual numbers. So example. So say that the probability of rain on any given day is 0.1. Okay, so if you in 2-week span, what is the probability of exactly 3 rainy days? Okay, so it says probability of rain on any given day. So it doesn't matter if it rained the day before. Today, it's going to be the same probability. So this is referring to the independence. So we can use a binomial distribution, right? So probability of rain in any given day, we can say that success is rain, so P can be 0.1. And 2 weeks spent, so how many days are in 2 weeks? So N is going to be 14, and we're looking for exactly 3 rainy days. Alright, so this is going to be, first, if we can look back to the probability chart, but I mean the formula, but this is going to be 14 out of 3. We're choosing 3 days out of 14 days, and we want probability success, we want them to be 3, right? And we want the failure, which is being sunny, to be the rest of them. So that's going to be 11 days. So this is the probability of x equal to 3. So if you multiply this out, you'll get the answer. So this is how you would use binomial distribution. It's actually very simple, I would say. And let's look at, what shall we look at? Yeah, so I would say I would just do a simple, not really a proof, but okay. So whenever we have a distribution, now we know that we have to have some kind of parameters, and we have to see some kind of measures. And by measures, I mean the expected value and variance. So let's look at a general case for binomial distribution, how we would come up with the expected value and variance, right? So expected value of binomial distribution is very simple. So just think about a Bernoulli case. Let's think about Bernoulli first, because this is an easier version, right? We have success, and failure, right? Success with a probability of P, and failure with a probability of 1 minus P. And if it's success, you get 1. Right, that's how it works. So say if we have a coin, we're flipping a coin, so coin flipping, and X represents number of head. If it's success with a probability of P, then it's going to be 1, right? 1 head. And if it's failure, 1 minus P, or Q, it's going to be 0. So it's always like this. The setup is always 1 and 0, Bernoulli. So this is pretty much how computers are operating. You know, computers are a binary system, so it's only 1 and zeros, bunch of 1 and zeros. So this is how they would go with this. So if it's success 1 and failure 0, so it's a bunch of Bernoulli trials if you think about it that way, or a binomial distribution. All right, so if you have this, expected value is always the summation of x and p, or the probability, right? So in this case, this is just going to be 1 times p, which is p. So for Bernoulli case, so let's just write it down here. For Bernoulli, expected value is always p, and that makes sense because you're only going to succeed p% of the time, and that's how you get your expected value, right? So looking at variance, okay, variance. Again, formula for variance is second moment minus first moment squared. And since we have a first moment, we just have to find this second moment. Second moment is x squared times p, and x here is 1, right? So 1 squared is just 1, so this is going to be, again, p minus p squared. Alright, so this is a variance of x, and people just denote this as, because it looks better that way, you factor out the p, and you get p times p minus 1, and 1 minus p, and this is exactly p times q. Alright, so this is the variance of x for Bernoulli. And looking into binomial is, if you think about it, just repeating this n times, n independent trials. So binomial distribution, this is just going to be n times p, expected value for Bernoulli, because we were multiplying, repeating n times. So we would do that for expected value and for variance as well. NPQ. Alright? So this is the formula for binomial distribution. And again, for standard deviation, you would just take the square root. Alright, so let's do an example, and let's just look at an example right now. Okay, so let me just write down the question for you. Alright, so here I copied down an example for this question, so binomial distribution. So let's read the question first, and I'll let you work on it for yourself. So according to Mendelian theory of inherited characteristics, a cross-fertilization of related species of red and white flower plants produces a generation whose offspring contain 25% red flower plants. Suppose that a horticulturist wishes to cross 5 pairs of cross-fertilized species. Of the resulting 5 offspring, what is the probability that A, there will be, this is a typo, there will be no red flower plants, B, there will be 4 more red flower plants, and C, find the expected value and variance. Alright, so I'm not sure if you're familiar with this thing, but you know how in genetics you cross the dominant and recessive genes, and you try to figure out which is the genotype and phenotype. This is a type of thing that that also uses the probability as a factor. So this is an example. I know there are a lot of different examples for this, but I just wanted to show you that in genetics, statistics is also used. I mean, obviously, where everywhere else is used. So yeah, it's just an example. So work on this problem, and come back to it. Pause the video and just work on it. And once you're done, come back to it. All right. All right. So let's go over this problem. So it's crossing, right? The cross fertilization. So here we can say that X represents the random variable, or we could say that number of red flowered offspring, right? And for N, because these are the parameters that we need, N is 5 because we're doing 5 pairs and resulting 5 offspring. And what's the P? What's the probability of getting red flower offspring? And it just says straight up right here 25%, so that's going to be 0.25. And this is what we're going to use for the rest of the question. Alright, so what is the probability that there will be no red flower plant? So probability that x equals 0. Right? And if x is 0, then everything else not everything else, everything has to be white. And everything has to fail, so that's going to be q to the 5th power, or in this case, q is 0.75 to the 5th power. That's the answer. Right? And now it's asking, what's the probability that there will be 4 or more red flower plants? So this is x is greater than or equal to 4, right? And we can write this down again. And this is equal to probability that x is equal to 4 plus probability that x is equal to 5, right? And we can do this separately. So x is equal to 4. Since there are 5 cases, we're choosing, out of 5, we're choosing 4 of them to be success. And success is 0.25 to the 4th power. We need 4 of them to succeed, and the rest is 1, right? And for probability that there will be 5 of them, so all of them has to success, so that's going to be 0.25 to the 5th power. Alright? And if you add this up, this is 0.015 plus 0.001, so this is going to 0.016. Right? And using expected value and variance. Again, formula for expected value. We just did a proof before, so I'm not going to do this again. But expected value for binomial distribution is always n times p. And for variance, we can do this first. So n is 5 in this case, and what is it? The probability is 0.25. So this is going to be what? 125? 1.25. Right? And for variance, as far as variance is concerned, variance is n times pq, right? So this is going to be variance. Find my pen. So variance of x is always npq. So this is going to be 5 times 0.25 times 0.75, and if you do that, what do you get? You get so these are the answers. So on average, you're expected to get 1.25 red flower offspring, and variance here is this value right here. Okay. All right. So that was that. Oh, and I did wanted to show you something. Let me just find that first. Okay, so this is something that we're going to do next. Okay, so here are 2 of them. Okay, so you can definitely use this. All right, so this is a simulation that I found. So what this shows is this shows the graph depending on how many trials you have and what the p is. All right, so let's just do this for now. So this is I'm not sure if you can read this, but if a coin comes up heads with probability of p and is tossed n times the number of heads is observed as follows. So this is a binomial distribution. The example that we've using many times, coin flipping example. And here is the graph. So here you can choose what you want to do. So number of coin tosses. So here you can choose them, and probably you can choose as well. Let's just assume that this is fair, all right? And this is 0.5. So probability of getting heads is 0.5, right? So this is first trial, and this is a histogram. So this is 0.5 and 0.5, and let's just increase this number of trials. So if you do 2, looks like this, right? 3, 4. I'm increasing the number right now. 5, 6, 7, 8, 9, 10. So increase it to 20. 20 is the max. So it looks like this. So going back again, it looks like that, right? Where this is 0, x equals 0, and this is x equals 1. So it's 50-50%. As you increase the number of trials, it looks very symmetrical, right? And we're going to talk about this later today. But that's called the normal distribution. So if you increase the number of trials of binomial distribution, you're going to get something called the normal distribution, which is the single most important distribution in statistics. All right? So just remember that as you increase the number of trials, it looks more and more symmetrical, right? And this is where the orange dot is where the expected value or the mean lies. All right, so just remember this, and let's go back to our notes. So now we're going to talk about something called normal distribution. Oh, before I do that, I forgot to do one more thing. And this was for fair coin, right? And say if it's not fair, let's just change the probability of getting heads, right? So if you decrease the probability, you see the graph shifting towards the left side, right? But as you increase the probability, you see that it shifts to the right side, right? So as the probability increases, obviously the expected value or the mean will increase, and if you decrease the probability, it's going to be skewed towards right, and it's going to the average or the mean will go towards the left, right? So that's how you change the value. All right, so going back to our note, now we're going to talk about the normal distribution. Okay, yeah. I was just looking in some examples if there might be anything interesting that we might want to do. Yeah, I think we can just move right on to normal distribution. Alright, so as I said before, normal distribution is very useful and very powerful, and I'm going to explain why that is the case. So normal distribution is I'm pretty sure you've heard of it sometime. at least once in your lifetime. Normal distribution. We call this, sometimes you call that Gaussian, because this is the guy who came up with it, or bell curve. Alright, so all these names are here. But before we go into this, let's just talk about something called probability density function. Right? So let's just let's just move on to this first, because we need to define something before we do this, because so far we've only discussed the discrete case, correct? So for binomial, it was either x equals 0, 1, 2, 3, 4. It was never 1.4 or 1.44445, something like that, right? It was never the case. But normal distribution is continuous, meaning that it's, when we're drawing a graph, it's going to look smooth. So it's going to be a line curve instead of histogram. So for discrete case, we have a different name for the probability. Right? So in this discrete case, we use something called relative frequency, because we can actually count how many times it occurs. Relative frequency. But something similar we're going to use in normal distribution is called the probability density function. Alright, so this is for continuous as variable. And it's kind of hard to explain how it works, but just to note that when we are looking for the probability, so when we're given the probability density function, right, and say that it looks something like, I don't know, something like this. So say that this is the, before I forget, this is PDF. We call this PDF because this is very redundant to say probability density function every single time we mention it, so we're just going to refer this as the PDF, right? So say that this is a PDF, okay, and PDF, we denote it as f of x. So this is the f of x and PDF, right? Any given point, right? At any given point, say here, right? This is x, and this is f of x. The probability that the random variable x is equal to little x is always 0. Okay, let's kind of think about it. When we have a line graph, it's this value is 0 at this moment. So for probability density function, we always look into the interval, right? So when we are looking for a probability, say I don't know, say that probability of x is, I don't know, less than 5, and say that 5 is right here. 5 is, I don't know, 5 is right here, right? Less than 5. Then we always look at this part, the area under their curve. Okay? This is the probability of something happening. So we always have to give it an interval or give it a range in order to find some kind of probability for a continuous case, because it's never equal to 0, right? Whereas in discrete case, so this is the continuous case. For a discrete case, we have histograms, right? So if it was something like that, it would look like this. So here it's, I don't know, here x is 2, 4, no, just, right? So let's say that the 1, 2, 3, 4, 5, and 6. When x is 5, then 5 here, this value will be the probability that x equals 5. right? And you would just add them up for x is less than, I don't know, less than or equal to 5, right? But for continuous case, we always look at the area under the curve of probability density function. Okay, so that's something to note. And here are some characteristics in words. Alright, so probability density function, the PDF, or denoted as f of x, right? It describes the distribution of probability for a continuous random variable. Okay, and these are some properties, right? So the total, again, probability density function describes the probability. So total area under the probability curve, under the PDF curve, has to equal to 0. It's always 0, right? Because probability always has to add up to 0. So just regard the curve as the probability, right? And probability that x is greater than or equal to 0, a and less than or equal to b, is the area under the curve. The curve between a and b. Okay, and we discussed this before, and 3 f of x is greater than or equal to 0 for all x, because probability cannot be negative. Okay, and this is something to note. Doesn't want to go down, so I'll just write it down here. Probably that x equals a, I don't know, a, for continuous is always 0. Random variable. Okay, so that is the case. Alright. And now we're going to move on to the normal distribution. Okay, so the normal distribution. This happens when we increase the number of trials for binomial distribution, binomial trials, to infinity. Okay, so theoretically, when we have infinitely many trials for binomial trial, then we are going to get something called normal distribution. Okay, and again, that's the theory behind it, but we're going to learn something called law of large number later on. So there is a I would say the fixed number. If you go above the number, then we say it's approximately normal. Okay, and let's just look at the graph for normal distribution. Yeah, I'm going to do my best to draw this. So this is the famous bell curve. Okay, so this is a normal distribution, bell-shaped density function. So this is x again, this is x, and this is f of x. So this is a PDF for normal distribution. And as I mentioned before, PDFs, the normal distribution has a PDF, but I don't think we're going to use it, but I'm just going to write the formula down just for you to see. And this is a very long formula rather. This is 2 pi times sigma to, this is e to negative half x minus mu over sigma squared, right? For negative infinity to positive infinity. Alright, so this is the PDF function for normal distribution, but again, you don't have to know this. You just have to understand how it works. And the reason why we have probability density function is that I'm not sure if you took calculus. If you, right, so if you, let me write this down here. If you integrate this, right, and we get something called capital F of x, it's just a cumulative distribution function. Or the CDF, and this exactly tells you the probability that x is less than or equal to x little x. So this is why we use this this funky formula or the function to integrate to get the cumulative distribution function. But we're never going to do that because we have other tools like Excel and or charts that helps us approximate these values. And yes, we're never going to have the exact value, but we will get pretty close with this approximation. So let's look at the curve, normal bell-shaped curve, right? So again, since this is a symmetrical curve, okay, we're going to have the mean right at the center, or in this case it's the mu, because this is, we're looking at the population here, right? And again, parameter for normal distribution is mu and sigma. So the mean, quote unquote mean, and the variance, or the standard deviation in this case, so mu and sigma, right? So the nice thing about this normal distribution is that if you go, let me try to write this down. Draw this here. And here. Okay. So so this is mu plus 1 standard deviation, and this is mu plus 2 standard deviations, right? This is mu minus 1 standard deviation, and this is mu minus 2 standard deviation, right? One thing that's nice about this is that if you take, oops, let's go back to session 14. Okay, so if you were looking at the area between 1 standard deviation away from the mean, so if you're looking at this part, right, this is always, okay, so this is always 68.3% of the data, okay, 1 standard deviation away. And 2 standard deviations away is 95.3%. Okay, and if you do 3, I believe it's 99.7. So if you do, we didn't write this down, but if you were to write this down again, and if you do mu minus 3 sigma and mu plus 3 sigmas, this is going to be 90. Okay, so this is going to be 99.7%. Okay, so it's really nice because if you capture 2 standard deviations away from the mu, then you're pretty much covering almost everything, right? 95% is a lot of data, most of the data. And if you capture 3 sigmas away from the mean, then you're capturing 99.7%. So you're capturing most of them. Alright, so this is the basic features of normal distribution. And let's look at the simulation again to see if it makes sense. Right, so this was the binomial distribution. Oh wait, let me try to look for something. Okay. Alright, so this is a binomial distribution, right? And if you say, I don't know, let's just do 0.5 for our convenience. It's a fair coin, and if you were to do this many times, right? So this is a number of trials, just one. It's 1 point, right? But if you do, if you increase it 2, 3, 4, 5, 6, you'll see that the more we increase this number 2, you're going to see a curve that looks like a normal curve. So if we're at 50 right now, it looks normal, right? Approximately normal. So this is how this is where we're coming from when we say when n is large for binomial distribution, then it's going to look like a normal distribution. And that's the definition of normal distribution. When you increase the number of trials to infinity, then you will get normal distribution. And one thing that's really nice about normal distribution is that later on we're going to learn that it doesn't really matter what kind of distribution you have. You might have this funkiest, weirdest looking distribution, but if you have n, right, the sampling size is, if it's big enough, then it's going to look approximately like a normal. So it doesn't matter what kind of distribution you have. That's why this is a very powerful tool that's a lot of statistics incorporate, because normal distribution is something you'll get no matter what. Alright, so I was that. Should we do z-score? Yeah, maybe we should. Okay, so let's just dig into this. Let's see how this really works. Okay, so see that these are some curves, and we have something like, it looks like this, something that looks like this, and I know my graphs are not looking that great, but it looks like this, right? So all of them, they doesn't look like that, but they have same mu. And we're comparing the sigmas for everything. Which one do you think? So this is graph number 1. This is graph number 2, and this is graph number 3. Which one do you think has the highest standard deviation? Well, the highest standard deviation is obviously number 3, because it's more spread apart. This is more spread apart. And again, higher standard deviations says that this is more spread apart. This is more wider. This is wider than other ones. So if you're looking at number 1, the graph number 1, this one peaks at the mu, which means that this portion has the highest portion out of all the other graphs around the mean. And that's exactly what we're measuring through standard deviation. How far away are you from the mean? Okay, so again, lowest, and always remember, we're always aiming for the lowest variance. So the lowest here, lowest standard deviation will be 1 because it peaks at mu, has the most data at mu. Alright, so that's that. And so when we are looking at some kind of probability, how do we find probability through normal distribution? And as I mentioned before, the PDF formula for normal distribution is pretty complex. So we're never going to do calculus through that, because I mean, it's not that hard, but it's just a lot of work. So say that this is the PDF for normal distribution. Okay, and we're looking for, say, I don't know, I'm just making these values. Say that this is 5, and if you're looking for, no, let's not give it any value. So we're looking for, this is, no, say this is B and this is E, and we say we're looking for any values, the probability that X is less than B, then we would just find the area under this curve, this part, anything that's less than B. So everything up to here, we're just going to find the area under this curve for the probability. Okay, and if we're looking at A and B, between these two values, then we're going to look at the area under this curve. Okay, so that's pretty much the idea behind it, and there is a way to do this, so let's just talk about this now. Okay, so for normal distributions, you have two parameters again, mu and sigma, and it might vary very much, right? So you might have, I don't know, like 2000 as your mu, or you might have 1 as your mu, right? So there is a way to standardize everything, and this is called a standard normal distribution. Okay, and for standard normal distribution, is always the same. Mu is always 0, and standard deviation is always 1, and we're gonna make it this way, right? So although other things might vary, we are going to do some kind of algebra to change this, right? And this is notated as the following, like this, right? So to do this, to standardize everything, we use something called z-score, right? And the formula for z-score is the following. It's always x value, right? X minus mu over sigma. Okay, so for any observations you have, so for example, if you have 3 as your observation, then you would do the same for this, and you're doing this in order to make this happen. This is called standardizing. Okay, because if you're looking at the mu value, then you will get 0 for mu because you're subtracting mu from mu. And if you have you're dividing by sigma because you want to standardize everything. You want to reshape it. So, for example, if you have a graph like this, right? Dividing or multiplying by something always shifts. So this is a normal curve, and the original curve you might have was something like this. It's a little flatter. And if you divide by sigma, then you're going to make it narrower and make it a standard. And by subtracting the mu, you're shifting. So okay, so dividing by this, it changes the variance. So it makes it narrow or wider depending on the shape of your distribution. And subtracting by mu, this shifts center. Okay, so this is how you get z-score. And z-score is very convenient because if you're looking at the probability, you can use z-scores to approximate the value, right? So for example, if you let's just work on an example. So for example, for normal distribution of 60, 4, this represents mu and sigma. Find probability that 50 x is greater than or equal to 50 and less than or equal to 63. Alright, and this is a normal distribution. So we're looking at these two variables. I mean these two intervals. Okay. Okay, so graphing the curve, it will look something like this. This is a normal curve, and since 60 is a mu, so this will be 60, and we're looking for 55 and 63. So we're looking at basically this part, and we're going to do this by converting this to z-scores. Okay, so z-scores of 55. Let's look at this first. 55, again, formula is this. So 55 minus mu is 60 over sigma. Sigma is here 4, right, given. So this is going to be, so let's label this as z1. z1 is negative, what is this, 1.25. So this becomes negative 1.25. Alright, and z2, if you do the same, this is 0.75. So this is 0.75. Okay, and this is going to translate into a normal variable, standard normal distribution, and this is easier to find. So if you're doing standard normal, this is going to be negative 2.5 x and 0.75, and we do this by following. Alright, so this is the table that we have, right, from negative infinity to z. So what it's seeing is that, I'm not sure if you can write this. So it shows a graph here. So these are the z-scores, and the probability here represents everything up to that point. Every the area up to that point. So this is called the cumulative distribution. So you're adding all the area up till the z-score here. So for example, we had 0.75, right? So we're going to go to 0.7 and go across to 0.5, and now you see this value, 0.7734, right? So that's okay. So this is a standard normal. So again, standard normal has always mu of 0. We said 0.75 has 0.7734. So that means that the area up till this point is 0.77434. Okay, so area up till here at this point is 0.7734, but we are not looking for that area. We're looking for the area between, so between these two values, and here is negative 1.25. We're looking at this area, not the whole. So we have to subtract something from here. Alright? And one thing to notice from this table is that there is no negative value. But if you think about it, if you look at this graph, this is symmetrical. So everything, say we're looking at this part, right? Because we have to subtract that amount from 0.7735. This part actually is equivalent to this point, because this graph is symmetrical, perfectly symmetrical. So from 1.25, the area over here, this is the same thing as that. Okay. But here's a problem. If you're looking for z equals 1.25, this is going to give you the area up till that point. So it's going to give you this area if you're looking for 1.25. But we don't want that. We want the opposite side. So what you're going to do is, since everything adds up to 1, we're going to subtract that from 1. Right? So this is going to be a little clearer if you use this. So we use that as, we notate that as the following. This phi of z is equal to x is less than or equal to z. Okay, so say that we just found out that phi of 0.75 is 0.7734. That means that z score of 0.75, so area up till that point, is the following. Right? So, and we denote that as phi of something. And since we're looking for phi of negative 1.25, we essentially have it as 1 minus phi of 25, right? So in general, it's going to be phi of negative z equals 1 minus phi of z. Okay? So looking at this variable, this area, we're going to do this as follows. Since we have 0.7735, you just have to find 1.25. So let's go back to the table. So 1.25 is 8944, right? So we have to do 1 minus 8944, okay, which is 0.1056. So the area between these two the probability of x lying in these two intervals is 0.7734 minus 0.1056, which is 0.6678. So this is the answer. So that's how you pretty much work with the normal variable. Okay. So in general, this is a general formula. In general, it's going to look like this. If x is, and we denote this by this squiggly line is distributed. Okay. Normally distributed with parameters mu and sigma. Okay. Then the probability of x is greater than or equal to a and less than or equal to b is equal to probability of, you have to standardize, so subtract mu and divide it by sigma, and the following. Okay, and you would refer back to the chart. So this is phi, say phi of z. Okay, this is probability of x is less than or equal to z. Okay, and if phi is negative, right, then you would do you would do 1 minus phi of just z. Okay. Okay, so 1 minus phi of z. So that's how you would work with normal variable. And z-score is always handy. So we're going to use that. For Excel, as far as Excel is concerned, we're going to do that next class. So that's that. And I do want to show some kind of simulation that I have. This is not it. Okay, so this was the binomial. Let's look at these. All right. So this is what I meant before. All right. So say that we're just assigning random values here. Mu is equal to 15 and sigma is equal to 2 in this case. And okay, I'm going to make it larger. So this is the original graph that we have, but we're translating that into a standardized normal variable. So it's normal 0, 1, that's a standard normal distribution. So first of all, you subtract 15. So your mu changes from 15 to 0. Correct? So that's that. And then you're dividing by 2, so you're making it narrower. Okay? And that's how you get the standard normal distribution. But say that you had mu is -2, right? Then you would have to subtract -2, so you're essentially adding 2, so you're shifting to the right side. So subtracting mu part is shifting your center. And say that, let's move it back here, and say that your sigma was, I don't know, 0.6, then this is too narrow, too steep, right? So you would have to divide by 0.6 and make it look like this, right? And make it a little wider. So dividing by the standard deviation changes your spread. And this is a normally distributed function, right? And if you're looking at, so this shows the z-score. So if you, I don't know, if you do z-score of 0.88, and that's right here, right? Then everything to the left of that is the area or the probability. Okay, so that shows how the normal distribution translates. That was that, and another simulation. Oh, that's similar to that. Okay. So this we're going to talk about this later on, but this is how I mentioned before that if the sample size increases, it's going to look more like normal, right? So this is when there are 5 samples, and you see the histogram over here, and that's nothing like normal distribution. But if you increase the sample, you see the histogram changing, right? And it looks more and more like normal, right? And it doesn't matter what kind of distribution you have, right? If you increase the sample to, I don't know, I'm not sure what the max is, 10,000, then this is almost approximately like normal distribution. So that's what I meant by that. All right, and if you increase the standard deviation, the scale changes. I wanted to show something different, but anyways, it's not showing here. All right, so that's it for today, and I will post up homework questions, so please work on those. We're not going to have any Excel problems, but we will have some word problems, basic ones, for normal and binomial distribution. So work on that, and you can discuss that in class. All right.